Feeding the Andean sediment cascade is what we're going to deal with today in this lecture. And before I start, please allow me to acknowledge some of my collaborators who really strongly influenced the way I think about how a sediment moves through active mountain belts. This is Julia Pomerenke, who's the PhD candidate on this whole project that I'm going to report on. Svenja Rosenwinkel is a PhD student just finishing on a very similar topic in Central Asia. Christian Moore is a colleague of mine who's introduced me to working in South America and Chile, who you heard already, I guess, on erosion in the Bolivian Andes. Jan Blöte is a Potsdam product. Okay, he's now in Bonn University and working in the Central Andes. And of course, Stella Moreras from Argentina, who is really supportive of our fieldwork and analysis in Argentina. I assume that the strategy lecture series has made you sensitive about why it is important to study the mass budget of mountain ranges, right? Source to sink studies. So I won't reiterate here. What we're concerned with is what happens at the source. What processes mobilize sediment? What processes create sediment? And why is this potentially relevant, okay, for the sediment cascade? And in particular, I'd like to highlight today two different processes named rock glaciers and rock avalanches. And we'll see that these two come from completely different domains, but look very similar, which causes a lot of problems and a lot of potential for great research. But the motivation I want to use to kick off why we should study the sediment cascade is a pretty practical one. Okay? Where is this? Anyone knows? Almost. La Paz. Okay. So we can see that the cities of the world are pushing higher into mountains, and especially in South America, we can see that the fraction of people living in cities is actually going up in elevation and also in topographic relief. So the way you want to read these graphs is on the y-axis you have the fraction of the city population, right, from 0 to 1. And then like on a hypsometric curve, you basically have on the left panel elevation in meters above sea level. And here some measure of mean topographic relief expressed in meters. Superimposed on this plot is a time series, okay, the evolution of the urban population from 1950 to 2010. Okay, you can see that, for example, 60% of the global, the South American city population was living at elevations up to maybe 500 meters and so. And what we find if we analyze this time series, it's that the cities that are lying higher up in the elevation and the topography are growing the fastest. Okay, it's not necessarily the ones that live in the flat lands, right? So these circles should give you some rough idea where the growth is highest. And this indicates that the maximum growth of South American cities occurs at about 1,500 meters above sea level, a nearly tenfold increase in the population. And the relief, similarly high, 1,500 meters. Now, if you want to put La Paz into a context, it lies at about 3,000 meters above sea level, and it has increased its population by 5 times over the last 60 years, if you want. And another great example, of course, is Bogota, okay, in Colombia. Here's a little picture, and you can see the increase has been 13 times or more in those 60 years in the population growth. Close to active faults, landslides, what have you, all sorts of natural hazards. So understanding better what happens on top of the sediment cascade, right up where all the sediment is being produced, has a lot of practical value. One of the many cartoons that I think is nicely encapsulating what a sediment cascade means, I prefer that to the source to sink term, because a really important issue in the whole sediment cascade is that we store sediment in between, okay? It's not that your particles are being produced by volcanoes, by tectonic uplift and everything, and then they march their way down into the nearest sink. Very often they're stored in between, and these sediment stores can be quite important and make up a significant fraction of this presentation here. So the sediment cascade in its most rough and spatially smallest form is something we see here in the Patagonian fjords of Chile. Okay, you can easily imagine how a rock particle is tumbling down from this rock face. These steep forested slopes and right into the fjords, i.e. the nearest sink. A very short sediment cascade. But we now have the tools to actually trace this pathway of particles from their source to the sink for larger river systems. And this is work that we've been doing in the Himalayas. These are two major rivers in the Himalayas. This is the Indus and the Yalong Tsangpo. Okay, it suffices to tell you that they're large. But these are not river longitudinal profiles. Now these are cumulative sediment store volumes along the longitudinal profiles of these rivers away from the mountain front. Each of these circles gives you an idea of how much volume we estimate to be stored in huge valley fills en route along a longitudinal river profile. And what's quite interesting about this analysis is that more than 90% of the whole sediment volume that's stored in those rivers is located upstream of areas of pronounced tectonic uplift and high exhumation rates. Okay, mostly on the Tibetan plateau side of things, which you can think of as a rough analog to the Altiplano in the Andes. And you can push this sort of analysis quite further. You can try to estimate the volumes of sediment stored at the mountain belt scale, okay, just to get a first order idea of how much of the source to sink trajectory is actually being buffered, okay, where the material is being stored intermediately. This is an analysis that Jan Blöte has done, basically using a digital elevation model of the Himalayan arc, which we see here, which is full of flattish areas, right? Valley fills most likely. But in order to get a better idea of what's happening in the mountain belt itself, okay, rather than on the plateau margin, which is outlined in red here, he filtered a lot of these flat pieces to eventually arrive at what is one of the first mountain belt scale estimates of how much sediment is sitting around waiting to be eroded. Okay, so the top panel here is showing you once again the Himalayan arc, right, from the Karakoram up here to Arunachal Pradesh in the east. The color of the circles gives you an idea of how much volume each individual valley fill has stored, and the diameter of the circles gives you an idea of the mean thickness of these valley fills. And from this immense database, which in this case consists of more than 37,000 individual valley fills, right, you can do a lot of interesting analysis of how the whole fluvial network is able to actually evacuate this material, how much material is bound to be stored, and so forth. And then, of course, you can normalize the potential storage volume to give you an average sediment thickness per major catchment that is sitting around. Very useful if you're interested in regional scale mass balances of origins and how they evolve. Okay? If you compare it to what we know from geochronological evidence, in other words, dated valley fills, okay, if you pick all the dated valley fills, all the dated terraces from the region, and you come up with a cumulative distribution of these ages, okay, so this is the time axis, this is 0, this is 100,000 years, and this is the cumulative distribution, you can then start to think, oh, wow, that's really interesting. It's intuitive, but it's interesting that we have many, many, many young valley fills, right, and we have fewer and fewer older valley fills, which is a pattern I would probably predict for all major mountain belts. Now you can ask yourselves, what does this tell us? Well, you can invert the problem and ask yourselves, how long would it take to actually erode these valley fills, if nothing else? So we shut down completely the erosion of bedrock, of hill slopes, right? And we tell the rivers to simplistically just remove all the material that's sitting in those terraces and those huge alluvial fans. How long would that take? Well, you can have different scenarios, right? You can say, let's assume a rate of 5 mils per year, let's assume a rate of 2 mils per year, 1 mil, and so forth. So you can convert these ages basically into sorts of residence times. But as you all know, the residence time also depends on how well the landscape is trapping sediment, okay? The trapping efficiency. So in other words, the trapping efficiency of 5% would mean that of the sediment that's being delivered to one location, 95% of the sediment is leaving the same location again, and 5% are stored. And the whole idea of this exercise is now we can see which of these different scenarios fits the observed ages of the valley fills the most. So in that case, we would say it's probably most reasonable to assume something between 1 and 2 millimeters on average of removal rates or aggregation rates, if you want to return this, which would then translate into something of a residence time of, say, a few hundred to a few 10,000 of years, depending on the size of the sediment fill. So this is basically the bathtub model that we know from biogeochemical cycling inverted on sediment stores. We use the volume as a proxy of the residence time of how long the sediment is likely to stay in the landscape. Mind you, these are obviously average estimates. Okay? The big outcome of this is that all this material that we store in the mountain belt is delaying things. It's delaying the flow of information that's contained in sediments from the source to the sink. So if you're interested in paleoenvironmental studies and you look at proxies that look at sediment archives, they may be prone to some storage in between and some delay of the signal, you'll have a hard time trying to match the impact signal in the mountain belt with that in the foreland if it's been stored for several tens of thousand years in between. Okay? Now you could argue, well, if you want to look at the sediment cascade, right, you should start with erosion first, because every material that you store needs to be eroded somewhere. Okay? Gerald Zeilinger has told you some weeks ago about one method to estimate those denudation rate, which is from the inventories of cosmogenic nuclides in river sands that you sample at different locations. This is the area that Gerald had sampled in the Rio Grande and La Paz rivers in the Bolivian Andes. And if you do your maths based on these denudation rate estimates, you find that about 34 to 60 million cubic meters per year are leaving the greater catchments into the Amazon. If you do the same method for the Amazon, which colleagues at GFZ have done, you can estimate then that this particular mountain catchment is contributing about 10% plus minus in terms of whole flux of the Amazon. The great thing is you can now establish regional archives of denudation rates based on the cosmogenic concentrations. However, if you go deeper and you dig deeper into the analysis and see what are these denudation rates based on, the things become a bit convoluted. Okay, so we have here the denudation rate derived from cosmogenic 10 beryllium, right? This is a log scale. Okay, so here would be 1 millimeter per year. Okay, that would be 1/10 of a millimeter per year and so forth. And we have here a measure of how steep the channels in the landscapes are normalized regarding their upstream catchment area. These are the data points, and you can see most of these data points actually fit quite a sort of a nonlinear relationship. Remember, this is a log-log scale, so a straight line gives us an indication of a nonlinear relationship. The steeper the channels are, the higher the denudation rates become, at least for these catchments that are eroding not so fast. However, if we go way to the fastest denuding catchments, we suddenly see that this trend is breaking down, okay? And suddenly the slope of this regression line here that we use is almost next to zero. So in other words, in the really fast denuding catchments, we're losing the capability of using channel steepness as a predictor of denudation rates, okay? The landscape is eroding so fast, the channels are so steep already, you won't see any more increase if you steepen the channels anymore. So one could argue that the topographic fingerprints of trying to predict denudation are being smeared out of the picture. This is a well-known effect, and a lot of theory has been built around this concept of threshold topography. Okay? At one stage, the landscape is so steep that you cannot really increase it any steeper because it's at its mechanical threshold, and hill slopes will just collapse and produce high denudation rates. You can repeat the same exercise for mean catchment slope. Okay, so the steepness basically, once again we have our log 10 transformed denudation rates. Using a different technique, or we try to unmix all the different data samples, okay, and we find there's two credible clusters of data points. Again, one where we see an increase, a sort of a nonlinear increase with steeper slopes on general, we have more denudation rates. But then, somewhere up here for the fastest denuding catchments, we don't really see any more trend. You can see that here as the orientation of the ellipses. Okay, so the long axis tells us there's a strong increase with slope here, so it's slope-driven denudation. And up here, the long axis is really doing nothing. It's pretty much horizontal. So you could argue this bit is, again, a threshold topography. This is the same plot, the same data. The bigger the circles, the higher the uncertainties are. So if you wanted to tease out some information out of these denudation rates, you could say somewhere up here, topography won't help us anymore to give us unbiased information about denudation rates. Okay? But we want to go farther than this. We want to understand the inputs that drive erosion up there. Okay? And especially in the Andes, you have another way of generating sediment in the landscape. Okay, these are volcanic inputs. This is Chaitén volcano in northern Patagonia that erupted 2008. The biggest pyroclastic rhyolitic erosion in about 100 years. Okay, and it produced a lot of sediment into the sediment cascade. Okay, rivers were overwhelmed. Temperate rainforest, really dense jungle was obliterated, transformed into huge moving trains of large woody debris. Okay, the township of Chaitén nearly escaped complete destruction because all the excess sediment was transported by lahars that avulsed across the settlement, buried a lot of these houses, made them more or less worthless. Another side effect that we study here is not just the movement of sediment, but also organic carbon, okay, because you're in a very carbon-rich environment. And the number that we crunched out of this is that this particular eruption seemed to have mobilized about 100,000 tons of organic carbon and flushed them straight into the fjords, right, which are nearby and thought to be a really important carbon sink in northern Patagonia. So making use of a very short sediment cascade, okay, only about 15 kilometers long from the volcano, which you can't see here because it's obscured in clouds, to the Gulf of Corcovado in the Patagonian fjords, can help you constrain a lot about the significance of how erosion and input into the sediment cascade is relevant. And moving further north into the Andes, we have other examples of how catastrophic events matter in the sediment cascade. Rock avalanches. Okay, this is Nevado Escalante in Peru. May 1970, a strong earthquake shook the landscape, particularly these double peaks here, almost 7,000 meters high. What happened, you had several million cubic meters of rock and ice detaching, okay, and dropping over nearly 3 kilometers vertically, fluidizing during motion, more or less creating a large debris flow that plunged down here. You can see here from this historic air photo, the trace, the trim lines, and then the debris flow basically split in two major lobes. One of them overwhelming the town of Yungay, right here at 2,400 meters, just a few minutes after detaching from up here. And then once hitting the major river here, the debris flow further fluidized, but still traveled a long, long way for 150 kilometers as a major hyperconcentrated flow. This is a historic photo of Yungay before, and this is a historic photo of Yungay after the event. Okay? If you Google this up again on the digital globe, you can see now it looks pretty much like this again. Okay? You won't see much traces of this alluvion, as it's called. And you can see only a few buildings really survived this particular massive debris flow. And it happened right at the top of the sediment cascade. Okay? This is elevation swath profile. This is the Pacific Ocean, right? This is Nevado Escalante up here. And you can see the massive distance vertically that it traveled and horizontally. And this is still excluding all the way out here. So we have a lot of topographic side effects of earthquake shaking in this particular rock/ice avalanche. But we also see the importance of generating rapidly large amounts of sediment in the cascade. This is one of the remnants of the town of Yungay. I understand it's a very famous tourist destination. Just some numbers to put things into context. So once again, the whole thing detached at about 5 to 6 kilometers above sea level, dropped for more than 3, ran out, at least in the catastrophic mass movement phase, for 15 kilometers in a matter of minutes. Okay, 20 to 50 million cubic meters, at speeds that don't really allow any running away. So that's not an option here. Nobody really knew how many people were living in Yungay. There's widely different damage estimates. The trigger you heard. And the interesting thing, there's at least one precursor a few years earlier and in pre-Columbian times as well. So understanding better what these catastrophic inputs do is clearly a task for us to solve in the sediment cascade, right? You could easily, expand this list. This is Rio Montaro in Peru also. Look at the size of this thing. 20 to 40 times larger than this event, okay? Not so fast, but still, it dammed a huge river, created a 30-kilometer long lake that burst after several months, sending a huge outburst flood wave downstream, affecting hundreds of kilometers of Andean river systems. So the one thing that makes these catastrophic mass movements really interesting to study is there might be proxies of earthquakes, prehistoric earthquakes. They might help to independently expand or augment paleoseismological chronologies. Another example from the Himalayas, this is the Nilgiri in the main range of the Annapurna Massif, 7,000 meters high. We are about 12 kilometers away from this face, and these deposits have detached catastrophically from this face. Funnily enough, like in many other mountain belts, there's now a lot of settlements on this former debris mounds, okay? If you look at the sediment budget I showed you earlier, okay, the Himalayan valley fills, just by going through the literature and doing a meticulous search on the volumes of reported mega landslides of this type, you'd find that at least 15 to 25% of the valley fills might be of catastrophic mass movement origin. A little plot of the vertical drop height here in meters against the runout, okay, the horizontal. This is Nevaduas Gran, so once again, nearly 15 kilometers, and it dropped more than 3 kilometers. And these are two colleagues that occurred in recent years, Jammu Creek in southeast Tibet and Kolka Kramadon in the Caucasus. Okay, massive runout landslides. Look at this is almost 19 kilometers. Okay, at average speeds of several tenths of meters per second. So we surely want to learn something about these guys in the sediment cascade. Not only are they very rapid, not only might they pose a lot of hazards to people, but they also transport a lot of material in geologically instantaneous time. And people have been doing this. This is the central Andes of Argentina, and they have mapped in quite big detail rock avalanche deposits and argued that systematic clustering of these rock avalanche deposits might actually indicate some sort of regional disturbance, which very well fits to some sort of earthquake trigger. So studying large rock avalanches at the top of the Andean sediment cascade might give us some information about the locations of prehistoric large earthquakes. And then again, of course, there's not just the volume that's been moved. This is catastrophic landslides worldwide, okay, in the 20th century. Only 200 of them have moved almost 20 cubic kilometers of material, but it's also the death toll, okay? And this is greatly underestimated. Most of the fatalities that we have from landslides are ascribed to very few rare events instead of many, many, many thousands of smaller events. So each of these circles is one distinct landslide event in this time series here. And this has been long recognized, okay? A couple of years back, Dave Petley from the University of Durham then went through the catalogs of damage from natural disasters and found that the numbers are grossly underestimated. Alone in these 6 years, more than 32,000 people have died from landslides. So the social motivation for studying landslides in the Andean sediment cascade should be clear. But there's other motivations. Obviously, it's not just the landslides themselves that kill people, but the after effects, okay? If they dam large lakes, okay, These lakes will impound valley floors, agricultural fields, villages, what have you. If the dams fail at some stage, the lakes will burst catastrophically and send huge outburst floods downstream that transform into debris flows, which are even more destructive than clear water floods, destroying infrastructure, agricultural fields, settlements, and so forth. History in the Andes tells us that these outburst floods can travel easily over several hundreds of kilometers. The Rio Mantaro, I was telling you, the debris flow traveled for 800 kilometers, right into the Amazon. So not only do we want to know something about the failure history of these landslides, but also the stability of their deposits should they dam lakes. Okay, we want to know something about the history of those lakes. This has been a core research topic here in Potsdam since many years. Okay, many colleagues have worked on the evolution of those lakes as climate proxies and so forth. And of course, the challenge for us in the field is to actually identify those things, right? Here, a former rock avalanche dam, okay, here in the central Argentinian Andes. And very often you find, where you can see the rock scree slopes and everything, but you have a very hard time in actually identifying those deposits as landslides if you're not trained to do so. What makes these rock avalanches so spectacular? Well, they're large, all right, okay, more than 1 million usually. They're extremely rapid, which I mentioned. But the thing is that I want to really emphasize here, they're flow phenomena, okay? They're flow phenomena of fragmenting rock particles. In the classic theory, people argued there has to be some sort of water to lubricate. There has to be some enclosed air bubbles to lubricate. Modern theories discard this option and rather go for the fragmentation energy that is really trying to drive these things. We also know that they're seismically triggered. Empirical studies tell us they are usually associated with stronger earthquakes. In the Andes, we have also volcanoes, so we have a certain variant of these rock avalanches that volcanologists usually call debris avalanches. They have a higher water content and more clay minerals because of the hydrothermal alteration at volcanic edifices. And they're usually more mobile if you measure their drop height over the vertical reach or the runout that they produce. And this runout is really puzzling because it defies all sorts of static friction Coulomb physics that we know of. Okay? The larger the volume that is detaching from a mountain, the more far it is bound to travel. So the apparent angle of friction is ridiculously low, which means you need some sort of dynamic angle of friction to take into account. You need some theory to actually make these deposits, or the moving deposits, so mobile. This is Falling Mountain in New Zealand, the Southern Alps. The whole flank was shook by an earthquake in 1929. A huge pile, about 50 million cubic meters of rock dropped down into the valley, and you can see the deposit here is quite low, but quite hummocky. And this is only part of it. The rest of it traveled some 4 kilometers down valley in a few minutes. Some of these rock avalanches swash against opposing valley flanks, so you can do some kitchen physics, okay? You can use the swash height, okay, against gravitational energy, basically, to estimate the maximum velocity, and you find that the larger they become in terms of volumes, the more mobile and the faster they become, with peak velocities of more than 100 meters per second. Of course, one thing is we want to know whether they occur and why. And it's incidences like these here in the Philippines, okay, a major debris avalanche in 2006 that defies all our models of rock avalanches. We knew that we need strong rock masses, okay? If we have jointed rock masses, they're more likely to fail in small bits. We knew that we need some hanging wall shattering, okay? We need some proximity to faults. But what we didn't really know was that geochemical alteration might play a major role in suddenly triggering these major rock avalanches or debris avalanches here also during rainstorms, which makes the use as paleoseismological proxies limited. Okay? We know some major rock avalanches can also be triggered by rain, which is a bit of a worry. And the other diagnostics that we use for these rock avalanches are, of course, the deposits. Okay, very fragmented, very angular. Okay, breccia, basically, okay? The bedding is always preserved, which is quite interesting because it indicates that there is very little particle mixing during runout. And you have a lot of flow lobes and levees. Once again, I want to emphasize this flow for a reason. So these features are so distinct that on this particular rock avalanche deposit, whose source area you can see here in the background, we can easily infer that this particular block, because it's so well rounded, must have ridden on top of the rock avalanche all the time. You can use cosmogenic nuclide exposure dating to actually verify this, which we've done. Which, of course, is another issue, because how to date rock avalanche deposits, right? Exposure dating, let's go, chip off a little bit. But how do you know you're not dating the land surface instead of the event itself, okay? I've mentioned before, volcanic rock avalanches are more mobile. Just to demonstrate, for a given volume, they cover more area, especially in the Andes. Why? Because all the volcanoes stand out of the surrounding topography, okay? They have the volcanic plains around them. So if you mobilize a lot of volume of rock, it's bound to spread over a larger area than if you mobilize the same volume of rock in an enclosed Andean valley. Another interesting thing about this sedimentology, other than giving clues about the mobility of these rock avalanche deposits, is the jigsaw puzzle texture, which is quite diagnostic in the field, okay? You see very shattered but coherent blocks. And a quite interesting curiosity is that you see thin shear bands with evidence of flash heating. So in other words, you see layers of pseudotachelite in them. Now your alarm bells should be ringing because pseudotachelite is something you usually associate with tectonic faults. And indeed, if you look at different outcrops, such as this one, this is a sort of a little slip here on a river, you would argue, well, I can see some shear bands here, I can see some really wonderful undulating structures here, maybe some sort of rip-up class and everything. If you look at these and do your grain size analysis in thin sections, you'd find that the fragmentation of these breccia goes down to the mineral level. These are quartz grains here, okay? Check the scale. And you can see that even the quartz grains themselves show a lot of shattering, although they are coherent, right? So a huge range of scale invariance in this shattering, and there's no chemical alteration in this. Okay, they're physically shocked rocks, right? Which is really interesting because we've done some laboratory analysis and we find that this partial melting and this shocking requires that we have very high temperatures, obviously, greater than 1500 degrees, and we don't really need any water, as far as we can tell from Mössbauer spectrometry. And this has really motivated a much more detailed query into the stratigraphic column of large landslide deposits, but we find very little in the literature. Volcanology is much more advanced than that. They have really good stratigraphic sections. But just to come up with this shocking thing here, right? This is the fragmented part of the rock slide column, and this is where all the little shear bands come in with some pseudotachelite bands. If you do your grain size analysis, okay, this is the volumetric percentage and this is the grain size, and you compare your rock slide microbrexia with other brexias from fault zones or even from impact brexia, you have a really hard time differentiating which is which. So you have potential for confusing, if the outcome conditions are really bad in the field, any sort of gouge-like material, okay? In the worst case, you confuse a fault zone with a huge rock avalanche deposit or vice versa. And this confusion potential goes further. These are some fresh rock avalanche deposits in the Chugach Mountains of Alaska. And once again, I want to emphasize the flow-like deposits, the low-bed structure of these deposits, okay? This is the diagnostic of a flow-like movement of intact rock particles that are fragmenting in the process. If you didn't have any specific training, you'd probably say it's a moraine or something else, right? And this is a major issue in the Andes because they look very similar to other processes. See this yellow band that's filling the river here, the river valley, and these sorts of lobes? these are not rock avalanche deposits, these are rock glaciers. Okay? So completely different processes, we shall see in a minute. If you pick up any standard definition, you find that rock glaciers are lobate or tongue-shaped bodies of perennial, frozen, unconsolidated material that is supersaturated with interstitial ice and ice lenses that move down slope or down valley by creep as a consequence of the formation of ice contained in them, and which are thus features of cohesive flow. So in short, they're a mixture of rock and ice that is flowing. Okay? And the amount of rock is probably larger than the amount of ice. So they're really super, super, super dirty glaciers, if you want. Is what one part of the research community would say. Others would say no, they are a complete distinct feature of permafrost, okay? Perennially frozen ground. This is one example here of a rock glacier, and you can see quite nicely the different flow structures, the sharp contact with the surrounding landscape here, right? But you don't see much of the features that we associate with glaciers, other than the tongue-shaped formation. So why are these things so interesting? Why are these landforms so much of an interest? Well, for one, they look very similar to rock avalanche deposits. Okay? They share many superficial similarities. In this sketch, we see a long section across the Andes, the arid and central Andes. This is Patagonian Andes. And this is where the glaciers we would expect them. Huge tongues here in blue, and some ice caps further down south. But then we see somehow mixed in together, interspersed with them, these brownish rock glaciers. Okay, how do they form? To be honest, nobody knows. There's two basic schools. One of them thinks these are derived from glaciers, okay, from dying glaciers that have been covered by lots of debris, protecting the ice as a core, and then still sort of moving on and on and on. And the other big school thinks, well, maybe they have been derived from also landslides and rockfall, but because they're lying so high and in cold areas, in the pore spaces, ice is freshly forming. Okay, so the ice comes after the sediment, and then the whole thing starts to flow. In short, you can view rock glaciers as geomorphic fingerprints of sporadic ice-rich creeping mountain permafrost. Okay, we have varied shapes and origins. So we call them either talus-derived or glacier-derived. So talus would be sediment first, ice freezes in later. And the moraine-derived or glacier-derived ones, glacier first, glacier dies, sediment falls on top. Either way, they're very difficult to tell apart from the myriad of other deposits up in the sediment cascade, in the headwaters. Okay, they're different or difficult to tell apart from glaciers, debris-covered glaciers, okay, moraines sometimes, deposits from ice or ice rock avalanches or landslides, and so forth. Their significance, however, is, and this has been shown in a number of studies worldwide, that their toes, okay, the lower rock glacier elevation really hugs the 0-degree isotherm. So we can use them as thermometers in the landscape, if you want. Unless, of course, you can distinguish them from other deposits. See these guys here? Remember the ones from Alaska? In the worst of cases, you can't tell the difference. Where you go to the field and you find hopefully some ice and you can start to come about. But we really have a problem here in finding the difference. Next thing is they're quite as large, almost as large as many rock avalanche deposits. So what is the role for the whole sediment cascade? Several groups have looked at this. These are some of the rock glacier study areas in parts of the Andes, okay, also here down in Patagonia. So they occur widely, but systematic mapping is really limited. It's just really at the start of being researched, okay? Permafrost community is large, and a lot of people work on rock glaciers, but there's many, many more to be mapped. So what people do, they use high-resolution satellite imagery. They go into the field and try to come up with inventories similar to ones that we use for glaciers, similar to the ones that we use for landslides. And the trick, of course, is then to distinguish between non-debris covered glacier ice-cold moraine, structural detritus, and what have you. Okay, you can easily appreciate from this particular map the different color codes mean different types of sedimentary bodies or ice bodies that someone fresh to the business would really have a hard time distinguishing. Nevertheless, there's quite different processes up there working to sculpt the landscape. For those of you who have heard of the glacial bustle and permafrost degradation and increased slope failures in mountain ranges, this is really only two facets of the multitude of landforms and processes that are working to denude the mountains top down. Okay, so it's a bit more complicated than we admit every now and then. And this becomes clear if you map these things locally. This is just one rock glacier mapped, and you can see the different things. There's a glacier, there's an active rock glacier, inactive rock glacier, debris-covered glacier, a push moraine. Hell yeah, there's even lineaments. So it's a lot of difficulty to actually map these things in the first place. You can use photogrammetry, so different time slices to see how they actually change vertically, okay? Similar as you can do for glaciers, and you can see quite rapid changes. Many of these rock glaciers flow at velocities of between a few centimeters to a few meters per year. Okay, so they're active features. They actively transport sediment. And they occur in places where we may not really expect them. This is the Venezuelan Andes near the equator. Okay, this is at about 4,300 meters. And you can see this flow lobe in here. What is it doing up here? There's another one up here. So clearly there's very little in terms of glaciers. The landscape would have been glaciarized if you judge from the frequency of lakes up here. There's many, many more. What does this mean? Is that an indication of former permafrost near the tropics? Or is it maybe an indication of former landsliding because of earthquake triggered at a nearby fault zone? So what we're arguing is that looking at the sediment cascade from above, from the top, holds a lot of potential clues for both the climatic and the tectonic history, or seismic history, I should say, of different parts of the Andes. And it gets even better. The permafrost people, who are actually going to convene here in Potsdam in a few days, there's a huge conference, about 1,000 or so people, they use the distribution of active rock glaciers, okay, the ones that are flowing and have very steep snouts, to model the regional distribution of permafrost. Again, permafrost is a thermal phenomenon. It just means ground that is frozen throughout the year. You don't need to have ice to have permafrost. You just need to have cold temperatures. And interestingly, you can model this distribution quite satisfactorily using only elevation, in this case from an aster DEM, and potential incoming radiation. Excuse me. So in other words, everything that's really, really dark blue has a very high probability of being permafrost, whereas everything that's sort of going into the sort of cyan and whitish blue has a very low probability of being permafrost. And if you look at the models that people use, you see that for rock glaciers, you need elevation, the size of the contributing area, solar radiation, and so forth. So in other words, we can use these landforms, again, as thermometers and as proxies of the distribution of alpine permafrost in mountain belts. In other words, if you map these rock glaciers comprehensively over large areas, such as here as the dry Andes of Chile, and you look at the spatial density indicated here in these dark gray shades, so the darker, the more rock glaciers you have suddenly a very interesting tool of inferring not only how much the permafrost level has depressed in the landscape, but also about its relationship to the equilibrium line altitude of the glaciers. So you can suddenly link your glacial history in the landscape with that of permafrost as well. So you get a finer picture of whether the whole thing actually matches, or whether the glacial erosion that a lot of people believe to be really important in driving denudation in mountain belts is actually working well with the reconstruction of permafrost, of periglacial erosion, of frost tracking, of rockfall, and all these other processes that some believe are actually integral parts of the glacial bustle. Don't worry, this will be the last killer figure. This is another figure done by Jan Blöte. This is a cross-section through the northwestern Himalayas. Okay, so in gray you see the topography. These are all the peaks. And these are all the mountain river valley bottoms. And all these vertical arrows here, these rainbow colored arrows, are the vertical reaches of large landslide deposits, more than 600. And the one thing that should jump right to your eye is that almost all of these have detached in the lower half of the landscape. Up here, okay, indicated by this dark gray line, which is the median elevation really, nothing happens for some reason. You don't see any evidence of major mass movements. You see a lot of evidence down here, but suddenly up here it's dead empty. Now you could argue, well, this is because you have glaciers here, so you can't have much of a rock slope failure. This little blue code up here is giving you the density of glaciers, and it's really only a few patches of the landscape where we could argue this is covered by ice. What's really interesting, though, is these blue triangles. These are the toes of rock glaciers. And see how they hug the median topography throughout the whole landscape, more or less, regardless of rock type, regardless of precipitation, everything. It's quite interesting. So you could argue maybe above this median topography here, something is either not preserving evidence of large rock slides and rock avalanches, or they're simply not happening because of something is precluding their occurrence. Maybe permafrost, maybe some sort of glacial censoring. The key point to take away from this is by simple mapping the distribution of both rock avalanches and both rock glaciers gives you a lot of food for thought of actually rethinking how erosion not just works on the map view, but also in the vertical view of your mountain belt, right? The sediment cascade starts here, but where is all the mass movement that should actually set it in motion? It's happening in the lower part of the landscape. Modeling of the thermal response of rock slopes to temperature variation has also produced the notion of a frost cracking window, okay, at which the physical destruction of intact rock by frost processes, okay, frost thaw, freeze thaw processes, is most effective between about -3 and -8 degrees, depending on the model inputs. Again, if we look at the distribution of rock glaciers, this is the area of the rock glaciers, and then is the mini annual temperature, we find that we can distinguish between those that are outside of the frost cracking window and those that are within roughly the -3 to -8. So these would be cold ones, these would be warm ones. The color code is pretty counterintuitive, I admit. But the point here is we didn't do much with the data. We told the computer, please classify, and the computer classified without knowing anything about a frost cracking window. So again, there's a lot of potential in looking at the size distribution and the location of these rock glaciers to learn more about potential areas in the landscape where we have a dominant type of erosional process. In this case, frost cracking and maybe production of smaller rock falls that in turn would feed our rock glaciers. Maybe we don't need massive rock avalanches to produce rock glaciers. Maybe they feed from smaller, more frequent rockfall. And this is really how rock glaciers can be used not only as thermometers, but maybe also as indications of what's happening to erosion and sediment flux. In the Altiplano, for example, you have very high sublimation rates. So if you want to nourish your rock glacier with snowpack and ice, you have very little chance unless you cover the snow and the ice with a lot of rockfall. And a few people have ventured out here and used rock glacier budgets to actually infer the surface lowering rates in high Andean cirque basins, coming out with denudation rates that are quite high compared to the ones that you estimate from cosmogenic nuclides. And it gets even better. The current knowledge about Andean rock glaciers is that they cover at least 150 square kilometers. Okay? You can do the maths. You think they're on average about 10 meters thick, and you argue that even if they only move 1 centimeter per year on average, you're moving at least 1 to 2 cubic kilometers of sediment slowly through the landscape. Slowly through a landscape characterized by super high relief, steep slopes, frequent mass wasting, what have you. This is really challenging the way we look at sediment flux, because when we think of sediment flux, we think of rivers, right? We think of glaciers, we think of fast. Should the rock glaciers not move at all? Well, then they're storing a lot of sediment, okay? They're buffering a lot of this production. They're just collecting the material, but withhold it from the river systems. This is sediment yield that we derive from glaciers in Alaska. Not just from the glaciers themselves, but the stuff that dropped onto the glaciers, okay? So riding passively on the glaciers, and we found that even more sediment is actually riding on top of glaciers than is swimming in most mountain rivers. So this could be a viable process of actually generating a lot of rich sediment bodies, debris-rich sediment bodies in glaciated environments. And we think that rock glaciers might occupy a band of sediment yields in these first-order basins high up in the sediment cascade that produce much, much more sediment that most rivers transport in the Andes. Okay, so we are looking at the potential of having ignored for many years a viable sediment source up high in the mountain belts. But the problem, of course, is I hopefully convinced you that rock glaciers can be confused with pretty much everything else in the worst case. So how do we know that the sediment fluxes that we attribute to rock glaciers do not come from catastrophic events such as these rock ice avalanches that cover a lot of ground, several kilometers in these valleys, and then you have more rock fall on top of it, and you mix everything together. So in other words, attributing the sediment flux to a single process in these high Andean basins and other high mountain basins is really still a challenge. And to wrap things up, the final aspect why rock glaciers are really important, especially in the Andes and other semi-arid or arid mountain belts, is the proposition by some researchers that they store more water than glaciers do. Okay? Depending on the source, people argue that rock glaciers actually are the main source of water for people, for people living in Santiago de Chile, for example. Right? So all these high-lying cities in the arid Andes may actually draw a lot of their water resources from these. Okay? And there's a few emerging studies that try to estimate the volumes of water. And these studies have been criticized lately because they have a lot of implications not just for water resource use, but for natural resource use. Because a lot of mining is taking place and a lot of mining companies have disrupted part of the rock glaciers. Now in certain countries it seems to be law now to stay away from these rock glaciers because there are sources of water in semi-arid mountain belts. So to wrap things up, instead of some conclusions, I want to have some conjectures here. Okay, because we're still in the part of where the research that Julia is doing and we're all doing is building up different hypotheses. The one thing that we see for certain is that confusing rock glaciers and rock avalanches leads to misestimates, potentially of permafrost limits. We have seen that the permafrost distribution is modeled by rock glacier distribution. If we misclassify rock glaciers, we misclassify the limits. The paleoclimatic interpretation of many catchments may actually hinge a lot of whether we say it's a rock avalanche, whether it's a rock glacier, whether it's a glacier moraine, right? And of course of landslide hazard, because if we misinterpret something as a rock glacier instead of a landslide, we push down the occurrence probability that it's a landslide. So one first step that we will do is try to work out a classification method that is as objective as possible that allows us to distinguish between rock glaciers and catastrophic mass movements for a given area in the Andes. The second take-home message is that rock glaciers really challenge how we deal with moving or stored sediment in high mountains. If the rock glaciers are creeping, then they transport a lot of sediment, and we are in the process of quantifying how much. Surely it's the first order estimate, but at least it's the first order estimate. Okay? It challenges the point of sediment flux, because how do you find sediment flux? Right? The volume that you transport through a given point in time. If most of the rock glaciers are inactive, they're retaining a lot of sediment from the Andean sediment cascade. Okay? So the sediment has to come from further below, which would then really challenge the way we think about the glaciers or the periglacial and glacial environments in rapidly denuding the mountain belts top down. And finally, rock glaciers might store substantial water resources and with potential political implications and all the conflicts that may arise from that. So these 3 points, I think, are, for me at least, convincing enough to study more the deposits of mixed ice and debris in high mountains such as the dry Andes to get a better understanding of how sediment is being liberated, stored, and released eventually. Thanks for your attention.